We are going to discuss about the hybridization of a system where transformation is made an integral part of the fabrication of the graphics. Object hierarchy in transformation. This topic is extremely important for designing animations. Transformation in modeling. Position objects in scene, change the shape of the object, create multiple copies of the object, projection of virtual camera, and animation. Here, what you see is that I have taken a single object, that is a sphere, and scaled it differently. That is, I've used anisotropic scaling to create oblate shapes, and placing these oblate shapes at different location. This person, which looks like a human being, has been created. So every joints have been created by these oblate shapes. Now, what you see here is that this person has got this portion is the shin bone, which is shown in the green shin region of the person. And if the person lifts the leg up and would like to kick a ball, this object is is not independent. It depends on the previous object's position. I cannot straight away translate this object or apply transformation to these objects because it is connected to the previous objects. So there is a hierarchy in this system. That is, if I do not maintain the hierarchy, I would split the leg into two. So if this object, that is the thigh portion of the person, that did not rotate around the hip joint, it wouldn't have lifted this shin joint region, the shin region up to this location. So what you need to do is that a particular point of a particular object, either it has to be stitched to the world coordinate, or it has to be stitched to another object. If that coordinate of that object changes, if that coordinate of the object changes, it automatically goes and stitches itself onto that particular point. So if I move the thigh thigh region oblate, this automatically will rise with the object. Similarly, the leg portion will also rise with this portion since this is stitched with this. Same thing is with the hand portion, which is the end results. It totally depends on the other parts, that is the forearm, and you have got the back end, which is there. They all are dependent on each other, and this is the hierarchy of transformation. And how do I apply this hierarchy of transformation? Let us see how it works. Okay, so here I have got a scene. I see that in the scene I need to have positions of camera, light, background, materials, and object. Please note here, camera is important because I need to know the camera coordinates. Because if I want to transform from the world coordinates to the camera coordinates, I need the camera coordinates. I also need the position from where it is getting illumined. Later on, when we do illumination, we will see that how this position of the light helps us illuminate the objects in the world coordinates, or illuminate the objects with respect to the camera coordinates, because the camera is finally looking at the illumination. So the light reflected from the objects, coming from the light source, reflecting on the object, has to reach the camera. If it doesn't reach the camera, you don't see the object. Of course, I need to have a background. I need to design a materials. It could be textures, different textures, and finally, and not the least item, is the objects. So these were part of a particular scene. So when I describe a scene, I need to place all these materials into the scene, to say not only the objects but material, background, light, and camera. So here you have got a simple scene description where there is a orthographic camera position given, light position given, background, material, group of objects given in the GL code. So here you have got the class or hierarchy of objects. So here I have got objects like 3D objects like sphere, cone, cylinder, plane, triangle. But I could also have a group of objects. Group is a combination of multiple geometric shape put together to form a group. As we had seen in the earlier lecture, where I had used a Rubik's cube, which is a cube. I had used a sanitizer bottle, which is basically a cylinder, and the third object, which was a complex object with a crank and a cylindrical object. So this is a complex object which could be designed as a group. So here I have got how do I generate a group. So here you see a scene. I see that I have a table. On top of a table, there is a tray, a green colored tray, and on the green colored tray, there are two objects which could be two fruits. It could be an apple and an orange, which is kept there. And I have a chair which is blue in color. All these objects are connected to, to the floor, which is shown by the black rectangular or a thick line which is shown below. So now let us see different objects. So I have got one object which is the table, which is this brown table, which is made out of three rectangles or three boxes. So I've got box 1, box 2 and box 3. All these three things are grouped together to form the table. Similarly, I have got another group which is this group of this tray and its two fruits or two spheres on it. So I have box, a green box, a red or a red sphere and an orange sphere. All these are grouped together and they form my second group. Now these two groups are connected with each other. That is, this group is sitting on top of the table, and these two groups are placed together to form the group together. On the side, I have another group which is the chair, which is formed of three boxes or three rectangles. So here I've got the three blue boxes, box 1, box 2, box 3. These are connected together to form the chair. I cannot separate them out because they form the chair entity unless the chair breaks. So this is my chair group. This is my table with the tray on top of it with fruits, and I have the floor or the plane on which they are standing. So all this together forms a supergroup, which is the world group. In this case, this is the world group of my scene. So I have created a world group which connects. So I need to connect every object like that. I may need to connect different parts of the objects to create this supergroup. So this is a tree of the organization of the scene. Now here you see that how I would it's a simple example of this group. Here you see how this nested group has been placed in my code. So here again I show you these group in different colors which depicts the colors of the different objects which it depicts. So here you have got the thing. You can write every box, you could give its parameters, basically the 4 vertices which define, and you can define the colors by which it needs to be colored. So these are how you would define these objects. Right. So I have got here I could design the material. In the first case, the material is supposed to be there is a typographical error that this material has to be blue on top, and the material below, which is marked as blue, has to be brown. Rest is the same, and you have this grouping of the objects. Now I would like to create an animation. What is my animation? My animation is my chair topples, falls on the table, and the table moves forward. Please note this is my story. The chair topples, falls on the table, and the table moves. Now, please note the table cannot move before the chair touches it. So, one has to make sure that the chair touches the table, right? And you need to topple the chair. So, how will you topple the chair? You need to rotate by some angle theta all the boxes, the three boxes which form the chair. You need to keep rotating around by small theta until it touches the boxes. Sorry, touches the table. Now, how do I rotate it? Please note that the rotation, if this corner is the origin of my coordinate system, if I rotate the chair around this origin, the chair instead of falling will start flying. It will fly up and not fall. So to make the chair fall, I need to bring the origin at this location. So I need to do a coordinate transform so that in the new coordinate system, this corner edge of the chair is the origin, and then you apply the rotation, and after you apply the rotation again you do an inverse transformation and bring it to this coordinate representation and display the chair. So you keep displaying the chair by sandwiching between forward translation and inverse translation, this rotation. Now, how do I check if the chair has touched the table? We remember this vertex which is at the corner. Okay, now this vertex, and we know these two vertices. Say that VC1, that is chair vertex of the chair. This is vertex VC1 and this is vertex VC2. So we can find out the equation of the line of this. Now, using the similar method as Bressenham, we can find out the position of this vertex with respect to the line equation which is based on these two vertices. So when I see that this vertex is on the left hand side, say it is positive, so you will keep doing the iteration until this vertex goes on the other side of the line, that is the coordinate when placed in the line equation will give me a negative result. So you keep doing this part, and moment you see that it has crossed the chair, cross that edge, you know that the chair has touched the table and you need to move the table, otherwise the chair will move through the table. So what you do is that you move the table by an amount where the vertex becomes equal to 0. That when I put the vertex, it becomes a point on the line which is formed out of this chair. So you keep doing these steps, you keep moving it by some amount, or rotate the chair, then find this position and keep moving the table until you say that the chair stops and the table also stops. Now, what you have here is that as the table moves, it is not just the table that moves, since there is some amount of friction, or this good amount of friction. As the table moves, the tray on the table also moves with the table. If the table was a little slippery, it is possible that the tray will slip. That is due to the effect of first law of Newton, that is inertia. The tray will slip backwards. So you could show some amount of slippages if you like, but essentially what you know is that if I move the table, anything on the table will also move with the table. Right? Where as the earth is rotating, it is rotating with us. We are also being rotated around along with the earth. Okay, it's in a similar manner as that. So, so you need to accordingly apply transformation for this there. So if I see here, I have got the 3D objects. So I have defined the geometric shapes. I have also defined the group. Now I put a new character to this 3D objects. This is transform or 3D transforms, which is shown in red here, which becomes an intrinsic part of a 3D group in animation. So here you see when I design this group, I know where am I applying this transformation. I am applying the transformation of rotation of the chair or the falling of the chair here, shown here as transformation in red in the tree structure. And then I have a connection between this. When it touches the table, that is when the table starts moving forward, and this amounts to the table transformation. So here I have got these groups, and I have placed the two transformation. This transformation is due to the rotation of the chair, and it rotates, and each rotation I need to buffer it and place it. So this provides the rotation of the chair, and anything below this, that is the three boxes, rotate at the same time. So whatever rotation transformation I apply to the whole group, which is all the three chairs. All the three rectangles don't move on its own, on their separately on their own accord. They all move by the same angle theta as we rotate it. Okay, and please note that we need to bring the origin of the transformation to the edge of the chair or the axis from where the chair is going to rotate. Otherwise, the chair will start flying, not rotating. Similarly, when the chair touches, we put a condition when the chair starts touching the table, where we see the corner edge of the table crosses the line equation of this the backrest of the chair, and moment it becomes negative, I know that the table has to move, and it moves to a point where it becomes 0. So, and you keep moving it until some amount where the table finally stops and the chair also stops. Okay, so this is the scene which has been designed. But all these transformations are within the whole group, which is the world group, where the world is still static, and you have the ground which is still static, and you have this animation which has been designed here. Okay, so you have different things. So you have a nested thing like translate and scale over a sphere. You could do it as same as translate scale. This is positioning what the example that we have seen of the human being. If we take the sphere, we need to scale it and translate it and place it at different limbs of the person. And this is how you could do by translate and scaling every sphere and making the human body accordingly. So what we have seen is that transformation in modeling, adding transformation to a ray tracer and transforming ray handling and the depth T transformation, the normal and constructive solid geometry. And we will also see what is transforming the normals. We'll see that it is not always possible to transform the normal. What is a normal? Normal is the normal vector to a particular surface. This will become important when we actually do illumination studies, where you need to find out the angle that the light makes with the normal, and accordingly the illumination takes place.
We've used Object 3D to give us access to a few extra transforms in the chain. However, Object 3D is designed for another purpose that is extremely useful. What Object 3D does is create a parent-child relationship between two objects. Once an object is a child of another object, That child is affected by whatever is done to the parent. Here I'm showing a fleshed out set of parent-child relationships. The car has 2 doors and 4 wheels. Each wheel has a rim, a hubcap, and a tire. This is usually called a scene graph, as it defines a graph of relationships of objects in the scene. This whole tree structure is called the hierarchy, another frequently misspelled word, so get it right. With this hierarchy, we can do a lot. For example, we can move the whole car by applying a transform to just the parent. The other objects in the hierarchy will automatically be updated with this transform and follow along with the body. We can also affect objects within the hierarchy. If I change the wheel's rotation, the rim, hubcap, and tire will also be updated and move along. Under the hood, what is happening is that a series of transforms are being maintained. For example, for the hubcap, here's the series. There's the scale, rotate, and translate set for the hubcap itself, then another scale, rotate, and translate for the wheel, and finally a scale, rotate, and translate for this car as a whole. In practice, the scale matrices are not often used, as many model creators make their models to scale. The good news is that these complex series of transforms can be compressed into a single transform that does it all. It holds all the scales, rotations, and translations, plus anything else done. We'll show how this works in the upcoming lessons on matrices. That said, fixed hierarchies and the parent-child relationship they establish are extremely useful. Hierarchies allow most objects to be controlled in a natural way. I believe I've said this 3 times, so I'll invoke Lewis Carroll's line from The Hunting of the Snark. What I tell you 3 times is true. Personally, when I'm thinking through what series of transforms I want to apply, I work step by step. Perhaps the most important rule I can offer you is this. Once you've applied a transform, forget about it entirely. That transform's applied, it's history, and you now have some new object in a new position, possibly with some new location at the origin. Next, draw a picture if it helps. I usually do. Finally, once a transform is applied, where does your new object want to move from there? If you find you've messed up and the new object is not moving toward your goal, undo and try again.
.3D packages use hierarchies to link the rotation, scale, and position of objects to each other. If one object moves, the linked object will move with it. In the first part of this tutorial, we'll explain a basic hierarchy. Then we'll group many objects to a null for easier transformation. In the third part, we'll organize a simple scene with multiple levels. Hierarchies in 3D software are much like the folders in Windows that organize our computer files. In 3D, they're almost the same, but rather than organizing files, they categorize 3-dimensional objects. Here is a cube and a sphere. By dragging the sphere into the cube, we can create a hierarchy. This is called a parent-child relationship. The parent is the object that's on top of the hierarchy, and in this case, it's the cube. The child is on the bottom, and here, it's the sphere. Let's grab the sphere and move, scale, and rotate it. As we can see, it has no influence over the cube, which is its parent. Now let's transform the cube. See how the sphere reacts as if it's part of the cube? This is because it's inheriting the transforms or the rotation, scale, and translation of the cube. Let's unparent these objects and reverse the situation. This time we'll parent the cube to the sphere. Now the sphere is the parent, and the cube is the child. Notice how the cube has no influence over the sphere. However, the sphere passes on its transforms to the cube. Let's move the cube down a little and leave it in a new position. See how the sphere still affects it? Some programs also display this relationship as a node network, but it's exactly the same. It's just displayed differently. The arrow points from the parent to the child. Folder networks are usually used for hierarchies that inherit transforms, that is, the rotation, scale, and translation. Node networks also allow objects to inherit other attributes, like constraints, equation, and even color information. Nulls are objects that can't be seen when rendered. They're used much like folders in Windows, to mark, categorize, or to place object positions. They can be different shapes, most commonly a cross or a box. Sometimes people use curves or other objects as nulls. Programs can have many different names for nulls, like groups, dummies, or locators. Here, more than 200 objects form this car. If we rotate each object, the car breaks apart. This is because each object is rotating around its own pivot point. Here we're scaling the objects. To make it a bit easier, we can group all of these objects together by storing them under the null object. Now we simply select the null to rotate, scale, and move all the objects at once. Here's a simple scene consisting of a fruit bowl, table, and rug. Let's arrange the objects into a hierarchy with multiple levels. In this structure, the rug at the top of the hierarchy moves everything below. The table leaves the rug behind because the rug is above in the hierarchy. The plate takes the fruit because the fruit objects are below, but leaves the table and the rug above. None of the fruit affect any objects because they are all on the same level at the bottom of the hierarchy as children of the plate. We can even add a bug and put it on the apple. Now the bug moves because the bug is the child of the apple. Whilst this example is intuitive, these are all virtual connections. So unlike in real life, we can effectively parent anything to anything. So let's parent the rug to the bug and the bug to the orange. Now the bug affects the rug and the orange affects both the rug and the bug below. When creating our hierarchies, it's important to organize the parenting order sensibly. It also helps to name the objects correctly too. In this tutorial, we'll organize a hierarchy for a hover robot. There's two examples, one for flying and one for swinging. Here are some parts of a hover robot. Take note where the pivots are on each object. These pivots will be on the rotation points for each part. Let's arrange the parts into better positions. So here's our robot, but he breaks apart when we rotate each part of the robot. So we need to put these parts in a hierarchical order. Keep in mind we have a left and a right side represented by a capital L and a capital R. Left refers to the robot's left side, not our screen left. Let's start by parenting the upper arms to the robot's head. Now when the robot head moves, the upper arms go with it. We can also rotate the arms and they stay with the head. Here, we're linking the forearms below the upper arms. Now the head will move both the upper arms and the forearms. And the upper arms will rotate the forearms. Next, we can parent the spherical hands to the forearms and the claws to the hands. Now the head moves everything because the other parts are below it in the hierarchy. Let's rotate the left upper arm and see what happens. Oops, for some reason the claws have disconnected. If we look closely at the hierarchy, we can see the mistake. The claws on the right side of the robot are parented to the left hand, which is then parented to the forearm and the upper arm. Now it's easy to see why the claws come apart. The right hand even rotates the left claws. So let's reorder this correctly. Now we have a fully operational robot to pose in any way we please. We can even animate a hierarchy like this. Alright, so it looks like the robot would like to have a swing on this bar, but we have a problem with our hierarchy. In the current setup, the robot's hierarchy is ordered for flying and not for swinging. To swing the robot, we have to move the robot's head across and rotate the left arm back into position. This is difficult, and if we tween between the two poses, we'll notice that the claw bounces around, intersecting the pole. The head also moves in a straight or a linear direction, not in an arc, like we'd expect from a pendulum swinging action. The hierarchy should go from the bar through the body. Let's start with the left hand, then the forearm, upper arm, head, right upper arm, forearm, hand, and right claws. So let's bring the left hand out of the hierarchy to be the parent. Then parent the left forearm to the left hand, the left upper arm to the left forearm, and the head to the left upper arm. Notice that the left claws are on the same level as the forearm because they are all children of the left hand. We could shuffle the forearm to be placed on the same level but above the claws. This is fine, but it really hasn't changed anything. Shuffling without changing the parent level doesn't affect the robot's hierarchy at all, just the way we're seeing the display. The left forearm and claws are still children of the hand. Now that the hierarchy is in better order, let's try it out. Oh, straight away we see problems. The claws are intersecting the pole and the arms are breaking. It's not really working well at all. So what's the problem? It's that the pivot points are in the wrong positions. They're in the spots that work for flying mode, but not for this swinging robot. So let's change the pivots to work with this hierarchy. We'll leave the right arm's pivots as they are, but the head's pivot can go to the left upper arm's old position. The upper arm pivot goes to the left forearm. The forearm to the hand. And finally, the hand pivot is going to go into the center of the bar, so when the hand pivots, the whole body will rotate around the bar. The left claws can stay where they are. If we want, we can adjust the grip with their pivots still in the same positions. So now our robot is set up for a swing action. He's much easier to pose and will work much better if we want to animate him. We even get a nice pendulum arc through the body. But before we go, let's have a quick look at changing a hierarchy mid-animation. Usually, we'd need a funky animation rig to do it properly, and that can be complicated to set up. Instead, we can use a simple trick to make all of this work. All we need is two identical robots. We've changed the colors on these guys to show them more clearly. The flying robot in blue has our flying hierarchy, and the swinging robot in orange has the swinging hierarchy. Now it's just a simple matter of turning the visibility of the flying robot off and the swinging robot on at the frame he grabs onto the pole. So here's the flying robot animating along. Now let's switch to the swinging robot. We've kept the colors on the upper arms to show where the switch takes place. And that concludes this hierarchy demo.